Good morning. We will talk about another topic in semiconductor, which you may find very interesting. Let's say when we are looking at particularly devices which are made of semiconductor, right? And that is the concept of junctions. What is this junction? How is it going to help me? And all of that, which we are going to see today. So as we saw till now, that okay, I have a good semiconductor, for example, and I could dope it also. Dope means that I could put some impurity inside it so that it could become that electron concentration are much higher than holes, or the other way is that your hole concentration much higher than N, right? And that is how we will call this either N semi or N silicon. If this is a silicon which we are talking about, and this would be your P silicon, right? And if we were to apply electrodes and electric field, you would see that you will see some conduction happening, right, between these. So what good this is? So let's say if you dope it N-type, P-type, what would be the application of such a device if you make it, right? So that is something you can think. So if we apply this, and this is quite nicely doped in a sense that there is some N. So then we see that N is much, if this is the case we have done, that N is much higher than P, which is the N silicon. We see because when we apply a voltage, what is going to happen? We are going to see a current, which is going to be our Jn, which we have talked about in another video of the drift, which is proportional to the electric field or the voltage which we are applying. So that would be your Q, and the charge, basically how much charge density you have, and what is the velocity. And velocity is your mobility into your electric field, right? And if it is quite nicely doped, then we could assume that your electric field which is there is N mu N, and this is V by whatever is the length of your semiconductor, right? So this is the L, because in this what we have assumed, because we know that your E is minus dV by dx, right? This is what we have discussed in the another electrostatics video. So from that point of view, if we say, okay, electric field is in this direction, right, which is what we wanted to see. Now, what is the V1 minus V2 and X2 minus X1? That is X2 minus X1. That is what you are going to look at. And then you can see that the magnitude of this Jn would be this much, right? So then one can say, oh yeah, I mean, now your current depends on your electron density, which is coming from, let's say, largely from doping. There's a mobility, which is the material property or material property, which we have to still yet to talk about in another video, because it deserves a full video. What is the significance of mobility? And the voltage which we have externally applied, right? And whatever is your length of the semiconductor, that is the scenario which we are in, right? So now if you see in this scenario, what is going to happen is that if I were to calculate, so J, I could expand also in current divided by area, right? So then this would become equal to Qn mu n by L, right? And this is the thing, which is what I could now say that, oh, this, the whole thing basically looks like that I is proportional to V. And if you have seen electronic component, it maybe reminds you of something, that I is proportional to V in this relation, right? So that reminds you of Ohm's observation or Ohm's law, which we know of, that what he did, he had different conductors, he was playing with different conductors with different diameters and so, and then he recorded V by I, that how is the V and I changing, and based on that he concluded that this is a direct relation. And then he said that V basically is equal to IR, or I is equal to G into V. R is what we call is the resistance of the wire, or whatever material you are flowing this current through, and this is what we know as the conductance, right? So from this analogy, you can then calculate that I equal to GV. This means G is equal to, you can say it's Qn mu n, right? Whatever comes A by L. That becomes your this. Then you can see from this, you can also write in a resistance. The resistance would become 1 by Q n mu L by A. Right? And now if you do this experiment, which is what he also did, he looked at different lengths, different cross-section area and everything. So from that, you can also relate that basically this depends on one of the key property of the material. That's what we say, this is a material property, right? So then you see, oh, now my rho of the material is basically decided by this Q mu n into n, right? That is what this resistivity or this is called resistivity. So there is a difference between resistance and resistivity. Resistivity is material property, because you see this is all the parameters in this which are defining this resistivity are material parameter. While these are L and A, they are dimensional parameter, right? So they are the structural parameter, which depends on how thick is your wire or how long is your wire, right? So that is what the structural parameter. So that is how you have to also in semiconductor, when if you are studying, you have to in your mind think what is the effect which I am seeing is coming from the structure, and what is the effect which is coming from the material, right? Because sometimes you may mix them, and that is one of the important thing when you are analyzing any semiconductor device or system. You have to separate it out, what is coming from the structure and what is coming, and this is typically done with the design of experiments, which is what Ohm did, right? So he had a design of experiments. That means he had different kind of wires with different lengths and areas and different materials he was playing with, and that is how he came up with this. Oh yeah, this is how the relations of the I and V holding right together. So that is just a segue that we saw. Okay, now the what is this semiconductor can be used as? So you directly saw that what is the application of this semiconductor would be as a, if you want to use, you can use it as a resistor, right? So that means we can make resistors, not just the resistors which you use typically in the lab, made with some different material, not the semiconductor, right? But these are the resistors one can make using your silicon or the semiconductor on the chip, right? So that is what typically on chip resistors you can make using just this doping of different semiconductors, right? Or different. So you know that if you want to change the resistance, though L and A is something is in the control of the designer, but in the material also you have a choice to how much dope do you put, right? And the mobility of the material which is coming, that defines this resistor. Is that the only use of the semiconductor, that we can use them as a resistor? Okay, good. You said, okay, this is the material. I put the contact, I can use it as a resistor. I want to do more than that, right? We saw already one of the structure where we were designing transistors, right? But there is a whole journey to come to transistor. Before that, one needs to look at, is that the only functionality that this semiconductor can give, which is a resistor, or can I do more than that? And then you see that, yes, there is one interesting device or the basic, which is what the concept is. And first, let me tell you the device. What is the device? So device, if you have seen or you have seen in your electronics book, is your diode. I hope all of you have all of you have come across this amazing component called diode, which is very widely used in all your power electronics or even in your circuits or even in your chips, right? Like, so there are multiple application of diode, which is I think I would not be able to do justification there, but if you are interested, you can look at. I can give some of them. So as we saw, one of the diode was also used as a solar cell. So basically, It can be used as LED. It can be used to generate the thing, which is from the optoelectronics application. When we look at in the power, it can be used as rectifier, right? And multiple different application to protect as a protection device, right? It can be used as to regulate the voltage, right? Multiple application in circuits we are seeing. If we are using, so typically, yeah, these are used in you see your converters, so DC DC, which is what I meant by DC DC converter, AC DC converter, right? Or even in your power transmission, you will find this circuit in many places, right? So that is sorry, this component at many places. So there's this overwhelming. Now the question we are asking is, oh, I know how does it behave. So that means I know that the current and voltage, if I were to apply a voltage across it, right? So let me show you diode. If I apply a voltage across it, right, and I'm measuring the current which is flowing, and I record it carefully, what I will see is that this starts to increase after certain time or certain voltage. And then here it maintains nearly zero current. And until if I go much in the reverse bias or lower much negative voltage, I see there is a characteristic like this, right? So this typically happens after much larger voltages depending on your diode, right? So we are only going to concern as of now to this region, which is what we know as the forward bias, right? Forward bias means you have two terminals. Let's think of this as this is the anode which you have, and this is the cathode of the device. And you connected positive terminal to the battery to the anode, then this is the forward bias we are calling it, right? And if you are connecting negative to the cathode, this is the forward bias which you are calling it, right? And this is the region where you are calling it reverse bias because it's just the opposite arrangement which you have, right? So that is the at the component level that you are able to understand this component. But the question we are asking, and how do I make it, right? We have been talking about, and but I know somehow that it is made of semiconductors. And you have been talking about this N silicon, right? And you said, oh yeah, I dope it, and then can I get this? But I saw, no, I am getting a linear characteristics, right? Or nearly linear characteristics. So it justifies this, but it does not make it zero on the other direction. So if I were to plot this, right, and I apply to, and this is your N silicon, right, and you again apply a voltage and you are recording the current, right? What is the characteristic you're going to see? Likely is something like this, right? This is your IV, which is why we saw that this is a resistor, right? Because it's a linear characteristic. What is our goal is to build this kind of relation, or this kind of, how do I do that? That is the question one would ask. And that is where you have to see that one way, why it is happening is because, why does it give this kind of characteristic with voltages? Because if you change even the polarity, you see the initially, so what was happening here, let me draw that. So if let's say there were electrons, a lot of electrons, right? So this is the case I'm drawing when voltage is applied as it is shown. So you see that when there is a voltage applied like this, so the field is obviously like this, right? Let me draw the field also. So then the electron force is like this. This is direction F is. So electron is moving into that direction, and that's why current is this direction, right? But if I were to reverse this, right? So let's say instead of this, if I were to make it like this, right? So then you see that your electric field will be in this direction. And then the movement of the electron would be in this direction, which would give you current in this direction, right? That is what is going to happen when we, and that is why you would see that the electron will still move, right? Even if you apply negative or opposite polarity to this device, electrons will still move, and that is why it is behaving like a resistor, right? Because the movement is not restricted in any of the polarity for any of the polarity. What is the main concept of a junction or a diode implementation is that I have to stop the electron flow in another direction. So that means when I am giving a electric field like this and like this, let's say for this it moves, right? Movement of electrons or net movement of electrons, and for this electric field no movement of electron or no net movement of electron. That is what is the key, that one, when they are designing a device like this, that is what should happen. So now how would you restrict the flow? Because we know how to flow, right? When we apply the bias, we know that electrons will flow nicely in a semiconductor, like if you are just doping it one, like either P or N. But now the question is, how do I restrict the movement? And that is where the concept of a junction comes from, that if I want to restrict, that means I need to have some kind of way that I create a barrier. So basically it's like in a device like this, right? And this is, let's say for example, I'm calling it forward bias, right? So that means now when I apply, yeah, I mean, we can see from this just opposite direction I would make. So this is this direction, this is the, yeah. So then we want the net movement to be there, right? Of the, so that means if there is a positive applied, negative applied, we want it to be having electron movement or forward bias, electron movement, yes, check, right? There is another case which we are looking at, the same thing. And we are looking at, if we apply negative, that means positive is here, negative is here. This is what we are calling reverse bias, and electron movement should be restricted, right? So that means that when I'm flowing this here, the electron would nicely, so this is the electric field, electron should nicely feel that it is going towards the this terminal, from this terminal to this terminal, and that is what would constitute the current. Now in this case, I have my electric field is like this. So that means my electron should, if it is going like this, it should not, it should feel that there are restriction of the electron movement, right? Like this. So this is not there. So for that, what do I need to do? One approach can be that I want to create a barrier for electron. In one case, this barrier is going away, right? So this is the typically you see the where the barriers come from in electronic devices or semiconductor devices. So barrier, this would be a solution that I can create a barrier when barrier disappears, let's say, right? Disappears when forward bias, and barrier appears when reverse bias. Now you say, what is going to happen? Oh, initially when I have, let's say, N silicon, this is the stage of the N silicon. This is my floor 0, right? This is my floor 1, right? So N silicon means that there are a lot of electrons which are there in this. And this is what we were seeing when we were applying any voltage, right? We were making the bottle like this. The electrons were flowing like that, right? But now we said that no, we want to restrict the flow of electron. That means somehow the electron should go away from that part, right? When we do that. And that is the another thing which you have seen. So this is our N-type semiconductor, right? Which is the other case is where you have a same scenario where you have the, let me draw with the blue one. So you see the same scenario for the other kind of silicon where floor 0, you see lot of holes, right? But in floor 1, you would not see electrons, right? Because they are doped. So that is why we call it p silicon, that there are net more holes than the electrons, right? So this is the case p greater than n. This is the case where n is greater than p, right? So now, is it possible by some way that, because I clearly see when electrons go to p or when holes go to n, they are going to feel a barrier. That is likely going to happen, because if you were to just combine these two, what is the scenario is, if you were to combine this, right, you will see this electrons, because they see, oh my god, there are no electrons here. Okay, so first initially you would see that they may go there. And why would they go? What would be the reason? If there is an electron movement from floor 1 of this semiconductor to floor 1 of this, think about it. We will talk about it in another video when we talk about the physics. There's a whole movement, but we have talked about the basics of it. So you can see, if you want to look at again, the hint is look at the diffusion video, right, where we talked about this. The whole movement would happen to the floor 0 if we combine this. But at the same time, can this provide a barrier or not is a question we have to explore, that what is happening when you are telling that this barrier, if I combine this p silicon and n silicon, and you are talking about that I apply a positive voltage or negative voltage, this barrier is disappearing and barrier is appearing. Can you tell me more about how do I understand this barrier? Because you are trying to make, and this is what we see, that there is a different semiconductor when we have, which is the concept of a junction, right? That means you are adding two different kind of property of semiconductor together, which makes this junction, right? And this is going to be the heart of many electronic devices which you are going to see, right? And diode being one of the device. And we will talk about the whole physics of this diode, what is happening, what is this junction doing when we are applying these voltages. But that is how you see one can come to the concept that if I want to make a different functionality, this is something which is one of the key enabler in the all the devices. So thank you to everyone who are listening, and happy learning, happy growing. Each day we learn something new, right? And if you found some terms which were not really, it piqued your curiosity, do look into the internet. There are many other material. And also, if you find that I should cover something in a new video, please put it in the comments so that whenever I check out, I can record a video about it. Thank you. Bye bye.